let's get started. So I'm happy to introduce Dr. Ned Britt. He's going to be speaking today, and he's probably the first, I think, the first true rocket scientist we've had speaking. We've had a lot of people related to NASA Ames and various things, but he has a PhD in space nuclear reactors. He's done low energy plasma physics, and also the thing I think is cool is ion drives, which are electric motors that press about the weight of a quarter for force, and that's enough to move a satellite around space, and it uses just electricity. And he's starting to think of ways to experiment with this power source, perhaps on model gliders, or maybe using model gliders as a test vehicle for this. So that was the perfect entry into this talk today. He ran his own company. He was CEO of Space Power, and he sold that to Pratt Whitney. So he's been in the business, but now I think we can hear about his electrostatic propeller and maybe ways it might apply to some of the things we're interested in. So, thanks, Ned.
Okay. Well, I should correct one thing there. I didn't do much with flame-belching chemical rockets. We only did electric rockets, which were mostly targeted for use in after a spacecraft has been launched and into the vacuum of space, then an ion drive would do that. One of my colleagues, I want to note something about them from JPL, has been running the propulsion system on the Dawn spacecraft. And just last week, after years of operating, it arrived at the asteroid Ceres. It went and visited Vesta, and then now it's gone to Ceres. And if you've put a very low thrust for a long time, you build up large velocity. And the whole idea is miles per gallon here is low propellant. So I noted here a couple of colleagues who are some of the people that were involved in this when we did it back in around 2003 to 2005. Joe Crowley is a professor from University of Illinois, and he came out here because he was engaged in electro-static efforts for inkjet printing and had quite a career developing inkjets. He now lives down in Morgan Hill area up on the side of the hill by Anderson Reservoir down there. And I was buying his books, and then I realized, well, this guy's right around the corner, so I decided to hire him. And Kent Keister is a colleague of mine. Kent is a former fellow he was a professor at Stanford in the high temperature gas dynamics lab. He's an expert in MHD. But Kent's really kind of a wonder kid. He does whatever he wants. Right now he's living up in Cottage Grove, Oregon, building an airplane. He's built several airplanes and experimental ones. This one has a float body. It's not a float plane. The body of the plane floats. It's an amphibian one. And he did a lot of, these two people helped on the analysis of what we're trying to do. And we looked at some of these things that are hinted to up here, such as sailplanes, Global Hawk, a little tiny UAV, and a big sort of airship called Walrus, and I'll tell you about those. So let's have the first slide here. So, I should tell you about why this happened. At United Technologies Pratt Whitney Space Propulsion Division, I was the chief scientist there after they acquired our company, and this is what we were doing then. This is what we call the Hall effect thruster. It's a plasma jet that is made of xenon ions, and you can see the actual device here. It's kind of a ring, like a angel food cake pan, and it shoots out a beam of ions at high velocity. There's a little bitty cathode up here, which you can see makes a small little plasma, and that's, if you will, the ground lead, because you're blowing out positive ions, and you have to eject some other plasma into the stream, which is rich with electrons, in order to make a neutralized beam. Otherwise, your spacecraft gets charged up and it turns into a fountain instead of a rocket. Anyway, we were doing this, and one of the people that is in another division of Pratt & Whitney down at Huntsville, Alabama, got to experimenting with these things called lifters. that were on the internet. I think we got a picture of those on the next one here. Yeah, this is not what he used. I didn't want to take anything that was actually proprietary, so I took something off of the internet. What this is a framework of balsa wood and real lightweight stuff like straws and aluminum foil. This particular one is a 3-stage unit. The one that I'm talking about was only a single stage, and it's an open frame. It looks kind of closed in this, but it's had a, and you can barely see it, but up the top, on top of these little posts, is a thin wire. And what these guys would do is take and build one of these things, and they'd hook a positive terminal of an old CRT tube, the old type tube of television. Take a high voltage line off the anode and put it up there, and this would be the ground, and they would create a corona discharge which would cause ion flow and create an ion wind, and these things would lift off. This particular one is generating 90 grams of thrust, and it probably was not very much power, but very high voltage. What Alan Minnick did, my colleague down there in Huntsville, was he built one of these things, and he actually measured the parameters. He measured the voltage that was applied, the current, and he varied those things, and then he would attach little weights to see how much it would lift. So that gave us the basis for being able to build an analysis of it, because we had the current and voltage characteristics and the actual thrust. The people who were at Pratt Whitney were interested to know if this had any potential for atmospheric propulsion. So we undertook an analysis of it, and it fell to me because I was doing that stuff in space, so they said, well, how about trying to see something in the air? So the next chart shows something. Okay, here's what we're talking about on this sort of a thing. Imagine a little, what we call an ionizer, something that has sharp points on it so the electric field concentrates there, and it creates ions in the air, and then it's charged positive at high voltage, and somewhere downstream you have a negative charge and negative terminal, and those ions are attracted downstream, and they collide with and impact normal air molecules and create an ion wind. I think you can actually buy fans like this now that work that way. Yeah, and they're not very much propulsion, but we wanted to see if you scaled it up and what the potential was. And the forces on the surrounding airstream obviously can generate lift, because people were making these little things fly up on tables, and they actually thought, at that time, some of them thought they were a mysterious anti-gravity force. But there are some advantages. If you could make an electrostatic propeller, it might have some specialized interest for things like unmanned aerial vehicles. There's no moving parts, so it's silent, it's stealthy. It's not limited by tip speed, and you don't have gyroscopic or torque sort of issues. And most importantly, you can build this thing to conform over some sort of a shape that could be an airframe. So we started to pay attention to this and use the data from Alan Minnick, my colleague at Huntsville, and they've got next chart here. So here's kind of an idealized area. Imagine a region which we'll call a duct, indicated by those two dashed green lines. And on the front end of the duct, we have some way of generating ions by a corona discharge. And on the other end of the duct, we have a neutralizer or an attractor. And the idea is that these ions would be drifted down through the air toward that neutralizer, and it would hit some of the surrounding air, and you'd also have the free stream velocity. So you have the airspeed inside. In general, the ion velocity is much larger than the air velocity. The ion velocity is about 100 miles per hour, something like that. And at sea level, it's different.
What kind of electric fields are we talking about?
We're talking
average between those plates.
Well, we're talking about maybe tens of kilovolts across about a couple of inches, that kind of thing. But we were investigating things over a wide range, up to meters in size and so on. But this high voltage power supply needs 10, 20, 30 kV and distances that are like your fingers and stuff like that. Now, so that's kind of the idealized concept that we use to imagine this. The next chart shows some things. I'm going to ignore the equations here, but I want you to just take a look at this. You can analyze that simplified thing if you ignore the free stream velocity and just say the ion velocity is so large you can forget the free stream velocity. And the thrust only depends on one thing, the electric field at the exit edge and the area of the duct. And that's a very simplified thing that you can find out. It's almost like you have a idealized plane where the pressure is higher on one side than the other, and so the flow goes through it. And the pressure is created by the electrostatic pressure, Maxwell stress tensor, which is this number, which is just the electric field at that area. Okay, so let's look at the next chart. Again, we'll forget the equations and look at the bottom here. The thrust over power is roughly inverse to the ion slip velocity. So if the ions are sliding through at a very high rate, then the thrust to power has a fairly large number, but as the free stream velocity catches up, the thrust goes down, but the efficiency goes up. So this is a expression that we used here and found out. Let's go some more here. This is the data from this fellow at Huntsville. He had measured the current and the voltage, and this is his data, and we fit it to a curve which says that the current is equal to a constant times the voltage, and the other parameter in here in parentheses, the voltage minus an offset. That offset voltage right there is the place where you begin to get some current. You have to get up to about 12 kilovolts in this system
To start ionization.
to start ionization. And actually, what he was using was a little thin 0.6 of a mil tungsten wire. We later went to thinking about things like carbon nanotubes, which I'll tell you about, in which case they would begin to ionize at much lower voltages because of field concentration around those tiny points. And then the current climbs kind of like the voltage squared after that point. And this, by the way, this curve is characteristic of electrostatic precipitators. That's a cousin of this device. You know, people who have these bagged precipitators that catch dirt and dust and move them into a bin and collect it. That's the kind of electric current they observe on those, and those things are quite very large. So we used that curve fit and matched it to where his onset was, and took some more data from it. This thing generated 6 grams of thrust with 13 watts of electric power. Now you can see that, and the currents are very small. They're less than 1 milliampere. In other words, a digit in that third position would be 1 milliamp, and the voltages are kilovolts. So that's the kind of thing you're talking about. Very high voltage, very low current, but not very much power. Okay, the next chart. So one of the first things that we thought about was trying to modify the boundary layer over an airfoil wing. And so the duct area then is along the span of the wing and some layer thickness above that, which is roughly the boundary layer region. And you can put these things in stages along the chord of the wing, so that you accelerate some ions here, you collect them, then you accelerate them again, and so on. You can collect them on down the way and make a multi-stage device. And we began to analyze that with more sophisticated mathematics at that point. That's where Kent stepped in. And the multi-stage ESP actuators turn out to be relatively efficient compared to an idealized propeller. I'll tell you more about that. And if this could work, you could not only lower the drag by keeping the boundary layer laminar for a long ways before it transitions to turbulence, but if you push it up high, you could actually generate thrust. And there's other things you can do too. You can also do this by having differential effects on one part of the aircraft and another to do things like banking it or so on. And of course, you can propel it forward. So this is one of the first things we took a look at here, I think on the next chart. Well, okay, this is some of the analysis from Kent Keister, where he took a somewhat idealized situation. If you think about a propeller of an airplane spinning, and you have some sort of control on it, so that you turn the propeller at a certain RPM, and you control the pitch, so that regardless of what you do about the airflow going through it, it always maintains a certain pressure difference across it. It now becomes, from the aerodynamicist point of view, an idealized disc actuator. From a mathematical point of view, you can treat this as like the propeller disc, where it has a pressure difference from the front to the back, and the air gets pulled through, and you'd have to assume that you change the rotation and pitch as you increase the free stream velocity. However, it always maintains that same pressure difference. And an interesting thing about that is you find out that the air which comes in at the front of the propeller and draws down to go through the disc and then comes out as a jet out the back, picks up half of its acceleration speed on the front side and the other half on the back side, which is kind of a surprise. I always thought it was accelerated out the back, but it actually accelerates as it goes in as well. And we compared the efficiency of electrostatic propeller as a function of the free stream velocity here for a number of stages. Now with a single stage, the efficiency is pretty poor. It's less than 1% efficient. But as you start raising the number of stages, and you get up here to, I think, this is the 10 stage here, this curve here. With 10 stages, you can see you can get out to about 60% efficiency if you start having the ion speed kind of coming up comparable to the free stream speed. So that gives some thoughts that, you know, that's not impossible, 140 miles an hour, light thrust, something is 60% as efficient as a idealized disc actuator might have some practical use. So we took a look at some aircraft after that. Next chart. Well, and here's the other thing. The force, the thrust, is very much greater when it's stalled. When it's stopped, it has a much higher thrust than when it's moving. And that's what this curve is here. And that means that if you wanted something to assist you in takeoff, it'd be effective. And it would be less effective for other things. I need to put a caveat in here. It may have an application in hypersonics at very high velocities with compressible flow and shock waves and stuff like that too. But we were thinking about low speed aerodynamics here. So how about the next chart? So the first thing we thought about was this thing called Helios. It has solar cells on top of it. And JPL and Aero Environment in Southern California were building this thing and flying it at Edwards Air Force Base, later at Hawaii. It has 14 big, slow-moving propellers on it, and it was made to go up to a very high altitude and loiter up there at a long time. Now, the advantage of this is there's a huge wingspan. So if you had something that was active over the top of that wing, you actually would have a very long, thin duct area, but a large amount of area and a substantial amount of thrust. So we did some calculations on that. I think there's a chart on the next thing about that. Yeah, so here's Helios. It has an 8-foot chord. It's got a 287-foot wing, and it had 56 pounds of thrust. We found that we could, with the same amount of power that it has, electric power, it's electric too, that's the other good thing, we could eliminate the propellers and generate twice the lift. But the most important thing was down at the ground, it generated enough lift to almost go vertically upward, which is one of the big troubles they had. So we didn't, the problem though was at 50,000 feet, you're at a low pressure And we're worried about blow discharge breakdowns that would not be a problem at either 1 atmosphere or at a high vacuum, but in the intermediate pressure, you got problems with easily ignited discharge breakdown.
You have an altitude sensitive
Right,
voltage.
right. You could do that, but really what you need is an altitude sensitive number of stages so that you have larger spacing between the stages. You skip some stages at some, as you get up higher, you're working over tiny little gaps. Because arcs at high altitude like to operate over a large area, but not over a small area. They have a pressure spacing product as the optimum breakdown. And if you stay away from the passion minimum, it doesn't break. Anyway, the management at Pratt Whitney, which builds big jet engines, looked at this and said, well, there's only one of these things, and you know, it's we're going to have to solve this breakdown problem if we know they can make it work. We didn't actually go after it, although we did talk to the people at Aero Environment. And unfortunately, Helios on a later flight in Hawaii just folded like that and went into the ocean. And so let's take a look at another opportunity. Next thing we looked at was Global Hawk. Global Hawk is has a very long wing on it. It's you can see this 3 view here that it has a long wingspan, and it has a turbofan jet engine in it. Has thousands of miles of range, I think almost about 10,000 miles. And we wanted to see if we could improve the boundary layer to maintain, all we're trying to do there was just keep it from transitioning from laminar into turbulence, what we could do to extend the range. And calculation on that indicated, yeah, for about 25 kilowatts of power, which is a fair amount of power, but considering you've got thousands of horsepower in that Rolls-Royce Allison fan jet, you could extend the range by 1,000 miles or more by just keeping the drag down low over that wing. And we talked to those people, but Global Hawk is built by Northrop Grumman, and Pratt Whitney sells engines. It has a Rolls-Royce engine in it, so once again, management didn't really want to go after that. Plus, it's a well-developed system that would require a lot of changes. But you might be able to implement that on some other kind of later version. Global Hawk Block 3 or something could have that kind of thing as electrostatic boundary layer control, and it would go a lot further and loiter longer over targets. Okay, we then took a look at a little guy. This is the pencil. And this is something called Black Widow miniature air vehicle, or micro air vehicle, I don't know what they call it. It's made up of these pieces. It has electric propeller on it. It's sort of a flying wing, not even round or bat-shaped or anything. It's just a trapezoid. And it has 3 vertical stabilizers on the bottom side. And I think they would, when they wanted to turn, it has a elevon right here in the back, which is like an elevator. I don't think it's segmented. I think it just goes up in one piece, and then they turn one of these vertical stabilizers to create a yaw and bank it that way. And DARPA has built this thing, and it's flying around as a stealth vehicle to go sneaking around over battlefields and stuff like that. But they wanted to have a better way to make it turn. So we were going to take a look to see if we could accelerate the boundary layer over this thing differentially to create roll and yaw in a coordinated turn. And so the next chart shows some interesting things about that. So if you put rows of these little pins with foil things on the top of it as the collectors, and you accelerated the ions like that, if you accelerate the ions on one side of the thing but not the other, you lower the drag and actually produce thrust on this side. And most importantly, though, you get an increased lift. And you also get a yaw because you're thrusting on this, or if you will, eliminating the drag on that side. And you can create a roll moment and a yaw moment. And we took a look at that for the Black Widow control. I think the chart next shows something about that. And it turns out the normal yaw moment that they had was only about 2 These are units of gram centimeters. It's a funny name for torque. It ought to be Newton meters or something, but a gram of weight on a centimeter lever arm. And the roll moment over here is out around 14. It did not make a good turn. It would turn like that, and then it would tend to just go up on its edge. But with the ESP in it, we could produce a 12 gram centimeter roll and 48 gram centimeter yaw with only about something like, I think, 14, excuse me, about one watt here, in here, half a watt of power. So it really was quite effective. A tiny little thing with only half a watt. The question was, can you get kilovolts in something that's you carry around in your hand? Fortunately, you can. There's a company up in, I'll tell you more about, that builds some little high voltage power supplies that are smaller than a matchbook. So the next chart here. Now we decided to go to take a look, and we talked to DARPA about that, and they said, well, you know, the place where we really need some help on this is in our big airplane, which is called the Walrus. This thing was an airship, which it's a lifting body, but it's also filled up with helium. And they wanted to make these very large aircraft, greater than 100 meters long, a cargo capacity would be over 100 tons. They would be able to take it and have it lift off with a whole Army battalion and fly to its location and then offload them and go back. This idealized picture here was one that was operating as a commercial outfit, and Lockheed Martin was doing this. So we went down to see the Skunk Works. Some of you probably know about the Lockheed Skunk Works, people who built the SR-71, the U-2s and so on. Not U-2. But it turns out the Skunks have moved. I got a next chart here. I put this guy's business card on here. It's now called the Lockheed Martin Astronautics Company in Palmdale. It's no longer down there, but they still keep a skunk on their logo. And I had to take this guy's, the chief scientist there, his name is Edward, and is also called Ned like me, so it can't be a bad guy. And I'm an Edward that's a Ned also. So we went down and talked to them about their Walrus. And they were very interested in this. He told us, he said, well, if you were to sit out on the back end, the aft end of the Walrus when it's flying, it's a great big thing. It's 300, 400 feet in dimensions. And the boundary layer is so large, you could read your Wall Street Journal out there, and even though it's cruising along at 100 knots, there'd be no wind. And your paper, you could turn the pages just nicely. He said, we'd really like to control that boundary layer. And so we started looking at masts of, 2 meters, 3 meters tall, filled up with little tufts of ionizers and macroscopic sizes to do that, and began to do calculations on that for them. The next chart I think is kind of interesting. They built a demonstrator for this thing, a subscale demonstrator. See the little skunk on the tail there. This guy is an airship that lifts itself, and it has gimbaled engines. It helps to thrust itself up, but more importantly, it thrusts itself down when it offloads the cargo because it wants to rise too high. And these feet on it are like air cushion vehicles, which they lift up when they want to cruise along and take off. But more useful is they want to pull it down so it won't go up when it's not when it comes on the ground. And we definitely had a good chance of boundary layer control with ESP on that thing. It has moderate speed and a big boundary layer, 1 to 2 meters tall, so you do a lot of stuff there. And we found out that, interestingly enough, we looked at the DARPA 2005 budget outlay, and they had called out in that thing electrostatic ion propulsion. And so we really started paying more attention to this. I subsequently believe, however, that what they really wanted us to do, even though they wouldn't tell us, was to make thrusters that were operable. If you coated the whole surface of this big giant balloon with points on it and stripes of electric actuators on it, you could make airflow in lots of different ways. You could make airflow down like that and help it go up. You can make airflow go up and help it hold down, and you can make it go forward and backward as it was flying. And because it has such a huge boundary layer area, this thing is wrapped around this whole big balloon. It does have a significant amount of thrust. Later I learned that Walrus was eventually canceled because of the problem that they couldn't deal with the extra buoyancy when they offloaded it. It would be heavier than air when it takes off, but when it lands in the battlefield where there's no terminal for it to land on, it comes down and lands in a field, and all the tanks and all the guys jump off, it wants to rise up. And when these things have sort of the opposite problem of a submarine. Submarine has a problem of going down to depth and going to crush depth and imploding. These have what's called a pressure altitude, where they go up and they expand, and if they don't then vent their helium, they'll literally burst. They work by trying to compress the gas into smaller tanks and let air in, just like the submarines take in water when they want to sink and then blow that ballast out and use air to go up. They fill up their bladders with helium to rise, and they try to compress that and let air go into bladders to sink. And I don't think they ever really solved that problem very well, although there is a company down in Tustin, California, I think a Ukrainian guy or some Eastern Bloc fellow, Igor Pasternak, is still building these things for commercial intention, and they have something in it called control of static heaviness, COSH, C-O-S-H. He has some proprietary compressors to compress the helium, at least he says, into bladders that will hold the helium at above 1 atmosphere, and then that leaves a partial lower pressure inside, and big inflatable air bladders that fill up and make it heavier, and then it would stay down, and they can control it that way, and then they let the helium expand. Not sure they're really doing that. I think they might be compressing air into the bladders and forcing the helium to go into the other bladders, but not sure how it works exactly. But it's significant that Tony Tether, who was the director of the tactical office of DARPA, when he left, went down there to work for those guys. So it may not be dead altogether. Anyway, we never really, even though they had money in the FY 205 budget, we were all set to go do that. Pratt Whitney closed down their facility in 2005 up on, if any of you remember being around this area back in the earlier days, they used to fire those big Titan rockets and it would rattle this whole valley. And they also were building Minuteman, mostly solid rockets up there, a few others. And we had been taken in by that group and placed at that because they merged with Rocketdyne, and they have a facility in West Palm Beach, Florida, and building the space shuttle engine, so there's a space propulsion division. But up here was just solid rockets. And they sold the solid rocket stuff off to Viacom, and they eventually sold off they then bought Rocketdyne, and they eventually sold that to Aerojet now. So they're pretty much out of that business. They're just building airplane engines now. And of course, United Technologies has a bunch of other things: carrier air conditioning, Sikorsky helicopters, I can't remember, Otis elevators and escalators, a bunch of different companies. So this, we never did really do this. The next chart I think maybe talks about that. Oh, well, we made a proposal to DARPA, and that's what I came to talk to you guys about. I'm here kind of as an evangelist about something that some of you hobbyists might want to take up. One of the things that in that proposal was to make analytical models of this phenomena, do aerodynamic tests and wind tunnels, like slow speed wind tunnels, and we were gonna do a demonstrator, and we had proposed to use a Pike sailplane, and that would have actuators on board the sailplane. Each wing would be separately wired so you could do differential control. And it was only one part of the activity, because there was a whole coordinated problem to build up something, leaving something that would eventually be a 6-foot tall boundary layer. But I think your sailplanes, one of them, if you wanted to, could be modified to do this and would increase its airflow over the top and have a lower drag, have better lift. And in fact, you might even be able to use it as if you had a electric wire on it and you put a lot of power on it, where you pull it as a winch, you might be able to power it as it's going up to gain some thrust with it. And so I want to tell a little more about how that would work. So the next chart. So the idea here is that you'd have these little pins. These guys here would stick up the thickness of the boundary layer, which is about a centimeter, maybe a couple of centimeters on some of the bigger ones. And what we were going to do was to try to find, you need to find tufts of very, very fine hair, metallic hair. The smallest thing I think you could probably make is carbon nanotubes. And we were teamed with a company that would grow those little nanofibers and mount them on these things. And you'd have rows of these pins, so I'm sticking up here, they're exaggerated, and stripes of conducting foils across there. And they'd be connected up with positive, negative, positive, negative, positive, negative, for multi-stage ESP actuators. There's a company in Sutter Creek, California, up in the gold country, called EMCO. They make these little power supplies about this size, 5 to 10 kilowatts, and only weigh 30 to 50 grams, battery powered ones. And the power consumption is not big. These things could actually, you guys carry batteries and ballast and stuff like that. You could probably find enough mass to help that out. And certainly you could get a lot more lift and lower drag. You also could have a system we envisioned where the little pins lie down when they're not needed. They only come up. If you had them on some sort of a hinge, you could lay the pins down to make a smooth top surface of the wing and then raise them up when you need to take them off. So I got another chart here on this. So here's some of the things I got to be able to read what I'm talking about here. See, here's the problem. Everybody up to now has not really done this in a systematic way. We began to do it only back in around 2005, because we had this one fellow who actually generated some data that we could use. And then we got some serious people involved, like Joe Crowley with electrostatic physics, Ken Kieser, who's a great aerodynamicist, and started looking into it. This, if you did it on a hobby apparatus and could demonstrate that it works, I'm pretty sure that some aircraft companies and the government would be willing to play along and give you more money to do it in a bigger way, because this has a lot of interesting things, and they recognized it at the Skunk Works. These things like silent operation and none of the issues associated with a rotating propeller, and you can make it fit any shape you want. The challenges are that you got to produce the ions with minimum electric power loss. And the trick to doing that is to have little points, but there's some other ways. You can have a low power RF discharge, like a Tesla coil that makes a little high frequency spark on it. You could go more exotic and coat them with americium or not promethium. What is the other isotope they use in the smoke detectors?
Polonium?
Polonium, yeah, polonium. Put polonium-210 and americium. Those things are alpha emitters, and they ionize the gas around them. And you could put some of those on there if you want to. And you would have to find out what kind of configurations of aircraft actually fit to this sort of thing. And of course, you need the small, low voltage power supplies. But there's help you can get that. These carbon nanotubes are now much more available than they were in 2005, or a decade later, and people can make a lot of those things now. The other interesting point is, if you have a series of discharge points and actuators, you don't have to turn them all on together to just make a smooth acceleration. I know of some people who worked in wind tunnel tests where they made a traveling wave. They would start the air flowing at the front, and they would reduce the voltage on that one, and they bring up the voltage on the next one downstream, and so that the air was moving through like a series of traveling waves. And that might be more effective at getting a bigger flow of air. The problem is, you can move ions, but you have a hard time getting to couple with the air molecules. And the other interesting point is, you might be able to, if you can spray any aerosols into the airstream, the large aerosol particles are very much more effective at interacting with the air. If one of these things had to fly through smoke or some kind of a mist, its thrust would pick up a great deal, because it would now interact with the air much better. But it could also, if it had an engine on it that was a generator of some sort, you could blow the exhaust out in there and have maybe some aerosol generated from the contrail, in a sense, is a resource in this case. And if somebody wanted to really get into this and build something like that, these people that I was talking to you about and myself, we'd be happy to help you go through the get down in the weeds for the nerd part of the analyze it.
What about problems of communications with the structure in, with this background electrical noise going on?
Well, if you had an RF discharge on the little pins, that's going to be a radio jammer.
Right.
But the other ones, the
DC
is
not a problem.
no, it doesn't emit an awful lot of stuff in that bandwidth. But an RF discharge is a broadband jammer.
Right.
Yeah, but that doesn't necessarily mean you couldn't shut it off during the time you needed to do something. But yeah.
So like create wind over the top of the wing, is that what happens?
You create a wind over the top of the wing. You can create a wind around any part of the fuselage, over the tail. You can potentially coat any surface with little pins and create airflow around it. But the most payoff comes by accelerating the boundary layer on the top and keeping it laminar and using that thrust. But you could also, in the case of Walrus, I think they want us to put it all over the whole vehicle and generate airflow to either go up, down, front, back in all different ways. And because they're talking about a boundary layer that's about this big. And you can throw a wind over the top or along, you can mount things along the side of the fuselage. You can have airflow along the fuselage.
But if you get a flow over the top, I know you get speed going forward, but you also get more lift down the wing too.
That's probably the most important effect, is that you, by accelerating the boundary layer, it doesn't transition to turbulence, so the drag is very low. That's the first thing. If you push harder and harder, it begins to be thrust. But before it becomes thrust, you get a much higher lift to drag coefficient. And so the lift is significantly increased on the wing. Those things have actually been demonstrated on little wing airfoil sections that people have run. Few people are beginning to make some experiments like that.
Can you explain the relationship between the height of the generators versus shorter ones versus tall ones, and maybe incorporating into a construction technique if they were shorter?
Well, the answer is they can be any size, but they are the sweet spot to put them is in the boundary layer. But if this were a wing, and let's say this table is the whole wingspan, and it was flying, the boundary layer would only be a small thickness here. And if you accelerate a sheet of air flow over the top of that, you'll do what Kyle was talking about. You'll create much more lift, and you'll reduce the drag by keeping it laminar. If you put something taller on there, you'll have a larger area, but the payoff for the energy spent in the part that's outside the boundary layer, that's sticking out in the free stream.
Dead.
Not dead, but reduced. It's diminishing returns. So we've concentrated on trying to work around the boundary layers in these things, but there's nothing that says you can't make it. And in fact, of course, the people who make these lifters, they don't have any boundary layer. They're installed. And so for static thrust, make it any way you want to. You make them poke out there and deploy them, put them back in again if you want to. So.
Do the attractors have to be surface mounted, or are they
No,
slightly off the surface?
They don't, but if we're talking about, say, air was going this way in the room, I wouldn't want to put the attractor like that. It would be
Right.
fine, but it would now a piece of drag.
That's right.
So I'd either like to turn it like that or like that.
That's what I'm saying, yeah, if it's like that, does it have to be a surface mount? Or
No,
does it have?
it doesn't. It could be up on stilts, or it could be a separate little, like a little
Standoff from,
yeah,
Could be underneath
a
the
little
surface.
canard wing or something above it, or above it or below
Could
it.
be underneath the surface of the.
Not so much, because you need to have the ions that are being forced along in the boundary layer to interact with it. One of the big things that needs to be done is to do two-dimensional analysis. We only did more or less along the streamline type of analysis, but you really need to get computational fluid dynamics and air and wind tunnels to understand the question about the transverse drift of particles as well as the axial drift.
Yeah, 'cause it's gonna start at the pin and
Yeah.
drift down toward this plate,
Right,
and then
right.
come back up
Yeah.
and drift down toward the.
Right. Yeah. So I don't know, I think there's another chart here, maybe. Yeah, on the airplane, on the sailplane. I guess the first row would be right near the leading edge we were thinking of. And multiple stages, if you use them, would be interlaced between the attractors. And they wouldn't have to be on the surface, but it's probably convenient to just put a little thin conducting strip of something on there. It could literally be a conducting paint, silver filled paint.
I didn't know if there was a ideal relationship with the height of your emitters and the attractors.
I think there probably is,
Yeah.
and probably it's not right on the surface, but if you raise it up, then I think it's going to be a drag source. The heights of them would be probably several times about equal to boundary layer things. The pins you need to have these whiskers on them as corona tips, and you need these high voltages. These power supplies could be used, and I was noting this, and if they used, that should have been not EMC, but ESP, is only used for ascent. You could supply electricity through a wire on your tow line and accelerate your plane as you tow it, and then drop it off. And you might also have pins that could be folded down during the gliding portion of the flight if you wanted to do so. So I come to tell you about this because I thought it might be interesting to think about sometime. And I would guess there's probably even a fertile opportunity to make a proposal to one of the small business innovation research things that the government puts out to do something like that and get some real money to do it if somebody wanted to do the other part. I think that's all the charts I have except for some backup ones. What's the next one? I've forgotten. Yeah. These are some more theoretical things that we had in there, which I thought we talked about if anybody wants to. Eventually, I think you'd go to a full CF computational fluid dynamics simulation with somebody like NASA. But they'd come along if these things gain a bandwagon effect when somebody starts demonstrating it and doing it. And it wouldn't be the first time that hobby people in aircraft have generated innovation that was absorbed by the rest of the industry. Yes, sir.
So on the thrust, what we were concerned is the launch part. So could it get enough thrust to launch itself, or do you need some kind of assist on that?
I think you could, but as I was saying, the issue there is if you want to have it launch at a high velocity like with your thing, I think you'd want to not carry that size of battery. But
It's a
you,
different need, right, for the fun.
but you could have a wire that supplies a large amount of power, and then once you disconnect, then you don't need it.
But we have a class called ALES, which doesn't necessarily have a very high power motor. It's just enough to take it up at a reasonable speed and
Oh,
get up
yeah.
to 200 meters and then turn.
I think that could be done. For a gentle ascent with just a slight amount of thrust, and especially if you could have some assist from thermals, yeah, you could use it for that, for climbing.
We'd be happy with a gentle ascent.
Max is 30 seconds,
Yeah,
200 meters.
okay.
So there's your.
No, we have a special ESP classification. That's all.
There's another one.
We got enough trouble with you with ALES.
Yeah, you know, we get contest directors and contest managers, you know, we'll come to that.
This could be,
We can have another fight?
Yeah, no idea.
could be right up there with helium.
Actually, I'm more sorry to hold the questions, but
No,
if you, the other thing that happens to my planes, maybe nobody else knows, we tend to land upside down or do various things. I imagine landing upside down would do a number on all these little nanotubes.
it could, and unless they were hinged so they would fold down. But they're a little short pin is pretty robust.
That's true.
As far as, but it would, if it gouged into the ground, something would happen that's not good.
You're just gonna learn about keep the shiny side up.
Need a little sign every morning.
Most airplanes don't fare well on upside down landing.
No.
All kinds.
We've all had a little experience.
Oh,
in that.
I used to fly radio control planes too, not gliders, but so, yeah, I dumped a lot of them in every way you can imagine. So, okay, well, I appreciate the chance to tell you about this. And
It's exciting, it's fun.
And if, as you think about it, if you got colleagues that are in the aeronautical engineering effort or have some ties and stuff at NASA or something like that, want to get something doing like that, and somebody's looking for more information on this, I carefully went through this and picked out all kinds of things that are non-proprietary and talked about it, glossing over level, but there's some people behind me who are a lot smarter than I am that could really help you get it figured out if you want to do something with it. All right.
Well, thank you, Dan.
All right.
Thank you. Yeah.